you're right. So this should, okay. So this should be, okay, let me just write whatever you said, okay? So this is sigma union epsilon, and then you read a stack symbol on the stack, and you decide what to put, what to
Yes,
put on
yes.
the stack.
This
Okay.
is what given in the Hofstra, even though other transition functions are also given in the different books. I mean, they have given this relation differently.
Hmm. Okay. Yeah, but is this also consistent with what was done in the lectures?
So in the lecture, actually, I'm little doubtful because they have used tradition of Sipser, and Sipser uses different notation. Sipser does not write this cleaning closure of tau in the right hand side. Sipser includes epsilon here in the right hand side. I vaguely remember, but then Sipser used to write tau and then along with this epsilon. So their relation is slightly different, and moreover, their definition is also different. Uh, it says that PDA is six tuple. Yeah.
So which of these elements is not there in the tuple, in their six tuple?
So I guess their Z naught is not given, and there the PDA can make a move even when it is empty, and then they used to design PDA slightly differently. I mean, in a different way also. Like they use one that special symbol as a sentinel, probably dollar symbol,
Mm-hmm.
and yeah,
Right. Yeah. I remember seeing that. Um, okay.
I used it because I found it easier to design PDA than to understand.
Okay. 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 Just give me a second. So this thing is behaving weirdly. I want to check whether the recording is happening or not. But one second. Okay. Yeah. Sorry about that. Sure. So let's maybe stick to this thing for now, just for the sake of consistency. Okay. So just read out the first language. This is the set of all um, 0 to the n, 1 to the m, such that n is at least 1, m is at least 1, m is greater than n plus 2, and you want to come up with a PDF for this. So how would you construct that?
So in this case, the number of ones is greater than the number of zeros,
Hmm.
minimum by an amount of 2.
Hmm.
So initially, I will keep on pushing all the zeros into the stack. And when I find the combination of 1 and zeros, I read 1 from the tape and 0 from the stack. Then I pop zeros from the stack and I keep on popping. And but that will not help because if so now then I'll have to ensure that I get at least two A's. So I read one A last A. I mean the equal number of I mean so n number of the ones have been consumed in this process, and now at least two more ones are remaining there over the tape. So when I read the combination of one from the tape and Z naught as the top of the stack,
Hmm.
so then I replace this Z naught as Z naught and I make a move to the next state. And then I should read one more one. And then I kept
Right.
keep on reading the ones and make a move to the final state. I think that will work. Yeah.
Yeah. Yeah. So if you are at Q0 and you see initially it's Z0. Um,
So can we write this notation like 0 comma Z naught and slash 0 Z naught, and that will imply that 0 has been pushed into the stack.
yeah, that's what.
and slash 0 z naught. So
You don't need to write the second thing, right? I mean, if we are just writing 0, that means we are just pushing thing on the top.
so that could be one notation. This
Yeah.
notation, which yeah.
Some textbooks do write like two symbols at a time. I don't know why, but
So which you use the notation in whichever you are comfortable with, right? Yeah.
yeah, sure. So this is our input alphabet. This is the stack alphabet, and this basically means we are pushing on 0 on top of the stack. So this is what we are doing, and then you could see. Uh, then maybe 0 is on the top of the stack and you read one more 0, then you want to push it again. So this is what we'll do.
Yes.
Okay, and now now if you see a 1 on the input and the top of the stack is 0, then you are going to pop the um,
Yes.
yeah,
Yes.
and now you keep on doing this. If you read a 1 and the stack alphabet is 0, then we are going to pop it. Eventually what would happen is you have exhausted, let's say you have exhausted all the zeros, and the top of the stack is at 0, but it is possible that there are still um some ones on the input tip that are yet to be read. Then what do you do?
So then the equal number of zeros have been consumed. Then I read one more one.
Hmm.
So 1 comma z naught, and I will keep this z naught as it is. I'm not going to push anything. Rather, I'll prefer to skip.
Hmm.
So z naught here.
Hmm.
So yeah, and after that, say I make a move to the state Q2,
Hmm.
and from the Q2, I'll add the similar I mean transition, make a similar transition 1 comma z naught and z
Correct.
naught
Hmm.
and Q3, and over Q3 I keep on getting, I mean, a loop here, more number of the ones. I won't make any uh, changes here, and eventually from Q3
Hmm.
I should read null
Hmm.
and null comma z naught, and then I will make a move to the final state.
Hmm. So hmm. Well, if you make Q3 itself the a final state here, that should also work, right? What do you mean by null comma z naught?
So null comma z naught would mean that I would be reading null from the tape and the entire input has been exhausted. Because in the PDA we accept strings in two ways, either through the
Right.
final state or by using the null store. So since I would be accepting the string through the final state, so the entire string has to be exhausted.
Hmm.
So therefore, null comma z naught would mean that I am reading null from the tape and then z naught as the top of the stack, and I move to the final state.
Sure. So, mm, okay. Uh, yeah, is this fine, Saurav?
Yes, ma'am. I just thinking that later I will just it is first class from yourself. So about PDF. So I am just thinking. So later I will confirm.
Sure. Yeah. So maybe we'll do more examples, and yeah, then you can ask. So second one is also similar, but okay, let's just do it. Or if you have some other language, we can do that also. So let's say L2 is 0 to the m, 1 to the n plus m 2 to the okay.
So this is like equal number of zeros followed by the equal number of ones,
Hmm.
and then equal number of ones followed by the equal number of twos.
Hmm.
So this is some kind of L1 dot L2 concatenation of two CFGs kind of thing.
Right, right.
Yes. So for that we can use the similar logic. So I push all the zeros into the stack, and the then I when I read when I start getting ones, I will pop these zeros, and so when all the zeros have been popped off, and when I read a combination of 1 comma z naught,
Hmm.
then I keep z naught as it is, and then I keep on pushing
Hmm.
ones into the stack,
Hmm.
and then when I start reading twos, then I keeps on popping off, and finally I'll have the combination of null comma z naught, and then yes,
Right,
we can extend it by the final state.
right. So basically idea is that you push all the zeros and then you pop um, so on reading 1 you pop zeros so that the 0 to the n 1 to the n sorry m thing is matched at this point. Now after that point you are going to push the remaining ones, and that would mean the remaining ones would be 1 to the n. And now you read 2 and pop ones so that you are checking for 1 to the n 2 to the n. So this is like concatenation of these two languages. So how will we do this? Q0, initially you read a 0 set 0 and you push it, then hmm, hmm, then you keep on pushing all the zeros. After that point if you see a 1 and the top is 0, then we will pop. But if you see a 1 and the top is z0, then we will push a 1 and we keep on doing this. Okay, and now you do the same thing again. You see your 2, the top is 1, then we are going to pop, go to q3, if you read a 2 and yeah,
And then finally we would be reading null, yeah, null comma z naught, yeah, final state. Yeah.
sure. Yeah, and I guess yeah, the third one is also similar, but let's just do it for the sake of okay.
So for this thing, I mean, when I push two A's,
Hmm.
I mean, for two A's, I need to pop three B's.
Hmm.
So how should I do it? So like if I read A, then I keep on pushing, I keep on pushing, and when I read a B, then I skip it. And then I read one more B, then I skip it. And then, but how to pop two symbols, two A's at a time? That's the issue. So when I read the third B, then I would like to pop two A's.
Hmm.
So how to do that? Oh, I can do it like this.
Hmm.
So yes. So say I push all the age into the stack,
Hmm.
and when I read a B, I skip. When I read another B, so I skip, I mean that all the A's have been pushed into the stack. When I read the combination of B comma A, I keep A as it is. I skip it in this sense. When I read B comma A next time, one more time, then I pop A. When I read B comma A combination one more time, then I make another pop. So and this skip and pop should have been done in a loop. Uh,
Right. So
and
you will have some state, you'll have some state that remembers, I mean, one state has to remember, okay, at this point I need to skip the B, and for the
yes,
next two times you are going to pop the
yes,
two A's
yes,
and you can loop it. Or the other way would be that every time you see an A, read an A, you are going to push three copies. So if you read 2n number of A's, then you are actually pushing 3 times 2n many A's on the stack.
yes, and that can also be done. And
Yeah,
similarly, while popping it off, I mean, we'll make both the things equal, six and kind of thing.
yeah, yeah. And then when you read a B, you are going to pop two uh, two A's from stack. I mean, yeah, both are essentially the same logics, just implementations are different. So how do we do this? You are at Q0, and yeah, so if we use this definition, I guess things will become easier for us. This thing, if you allow to push a string instead of a symbol.
Yes,
Uh,
yes.
hmm. So you see an A and Z0, then you're going to push three copies. Hmm. And if you see A and the top of the stack is also A, then also you're going to push three copies. Um, Finally, if you see a B, uh, you are going to, and the top of the stack is A, then we're going to pop it, and Q2 does that thing again. If you see an A, we're going to pop it. Sorry. Uh, okay. Okay, I think this is what you meant, right? Without reading anything, you want to perform an operation.
Yes, yes. So if you implement the other logic,
Hmm.
so that would be like a comma z naught. So I push. So instead of writing three a's, that would be simply a. I'm pushing all the a's into the stack.
Hmm.
So and then when I read a b comma a, I will instead of epsilon say I will keep that a as it is. Uh,
Wait, you have, sorry, wait, you have 2n many A's here, okay. Now,
so I have two n number of the a's, right?
hmm.
And Z naught is also there, by the way, at the bottom of the
Right, right,
stack.
right, yeah,
Yeah.
yeah.
So now I read a B from the tape. So then I will keep this A as
Yeah,
it is.
that problem will not occur if you do, yeah. So, let's do this way. You are at Q0 and AZ0, A, A is also A. Now,
Yes.
if you see a B, then doing, sorry,
So
uh,
at this point, probably we can do any range.
yeah,
No
you
issues.
can, yeah, you can push it and pop it again.
So this time it would be better if we pop it off. So b comma a and then epsilon, because then I would be maintaining a loop having two states, wherein one times I will escape and other time I will pop. So effectively corresponding to three b's, I would be popping two a's from the stack. So now make a move to the state q1, and
Yeah,
then
I.
from the,
Hmm.
yeah, from the q1, say if we read b comma a again, so then skip, I mean keep a as it is, keep a as it is, so b comma a, and then move to the state q2,
Yeah.
and on the
Sorry.
q2,
Yeah, this is a little confusing if I write A, because that in this notation that we are doing, this would mean that you are pushing A. So
oh,
let me just uh,
okay. Now from q2 you make a move to
let me
q1
just pop
instead
it.
of,
Yeah.
no, I mean it's from q2 you move to q1.
No,
Do not.
this whole thing that we are doing is that we're not changing anything. You push a B and then you pop it out. So at
Oh,
Q3, huh.
okay, all right. So I pushing b. Oh, all right. And then from q3 to q1, you make a move like b comma a, and then you pop it off. So yeah. And now, so in this loop, what would happen that one, so effectively corresponding
No.
to, yeah.
So this loop is not enough because here you are not making any change, and here you are popping. Whereas what you want is you want to pop twice and do nothing once.
So in this logic, what is happening that number of ages twice. I mean, in this case, in this implementation, corresponding to three Bs, I would be popping two As, and you
Yeah,
can check whether it is.
that is not what this loop is doing, right? In this loop, you are not doing anything once, and then you are popping once. Whereas what you want to do is you want to pop twice and not do anything once. So there should be
So
one more.
So how many B's? Because I mean, this is because of the problem in the notation. Otherwise, moving from say, if you slightly use this notation in a different way, if that can be used, so then like here, I read one B, I read one more B, I read one more B, I read three B's from the tape. And after reading three B's, how many A's have been popped off? So two A's have been popped off. But here, what is
Yeah,
happening that
so
you have read one,
the
two, three, four piece actually.
yeah, so that whole thing can be implemented by just adding one state here is what I'm saying. So you do this so that you are popping twice and then you are not doing anything once.
Actually, there is some issue with this because we do not have this combination b comma b. We won't be having this combination ever. I mean that is so
What
like
if
like like here what is happening. You are reading. If you see, then how many b's have been read from the tape? One, two, three, four, and five.
no, no,
Probably you
that
said.
is no, that is because you made this transition here. So then appropriately we will have to choose Q4 instead of Q1, because at Q4 you are making three changes. This is the first change, this is the second change, this is the third change. So whatever transition happens will happen from Q4.
Yes, but slightly difficult. Yeah, difficult for me to understand this. Uh,
Mm,
maybe because of these two things, b comma a and then b, and b comma b and then epsilon. Probably you want to create an aggregate effect that as if you push b into the stack and then you pop it off.
yeah, yeah,
But in,
yeah.
but in
So
this process, what has happened that you have read two b's from the tape,
yeah.
because in the PDA, the reading head will keep on moving towards right.
Mm-hmm.
So that has created a problem actually. So
Uh,
to create an effect of no change, something else may be done. But
no, what is an issue with this?
so in this case, the issue is that we have read two B's from the tape. So
Mm.
now the number of a disproportionate
Hmm.
number of bits have been read from the
Yeah,
table.
so then that, so, uh, okay, sure. Okay.
Uh,
Yeah, so, yeah, maybe, yeah, maybe you just need a notation for denoting
skipping.
that you're not doing anything.
Yes, yes.
Hmm. Okay, let's change this. Okay, so you see your B, mm, and the top of the stack is
Top of the stack is A,
A.
and then I won't do anything.
Hmm.
So any, you can probably write skip here, slash skip. Skip would mean that as if
Hmm.
yeah, yeah, that will work. So escape would mean that A is replaced by itself, kind of thing. And nothing is being pushed, nothing is popped.
Hmm.
And now from Q3, I can directly, so I mean, this Q4 state is not required, nothing is
Hmm.
required. Directly from
No, no.
Q4 to, yeah,
Hmm. Hmm.
a single this B is sufficient. So what is I mean, Q3 to Q4, having this label B comma A is epsilon. So now in this process, C1, yeah, like this. I mean, why to require this Q4?
No,
Uh,
you have to cyclically do this, right? You have to skip one B and push two Bs. Sorry, pop two A's.
So that is happening here because one A has already been popped off during this, and then two, and then three. Oh, I see.
Yeah,
Three.
you do. Yeah.
Yes, yes, yes. Yes, that's fine. But in this case, one, two, three, four. Oh,
Yeah, so that 4 is not an issue because you just um, sorry, yeah, because you just take the, I mean, take Q4 as your third state. Like this is one, two, three, and even if you do cycles like after 6 steps, you will still be here. So
oh,
Q4
yes.
corresponds to the,
Right, right.
yeah,
Yeah, that's fine. Yeah, correct, correct. And then from here, so finally, yeah, from over the state Q4, after making many moves, many traversals here, then on Q4 I would be reading the null comma z naught, and then I will make a move to the final state.
right, yeah. So yeah, so hmm. So just to repeat, because I guess yeah we erased this so many times. Basically, what we're doing is initially the top of the stack is Z0. So the top of the stack is Z0. You see an A, then we are pushing an A, and now if the top of the stack is A and you see more A's, then we are pushing them. Then some B's could come up. So if there's a B that comes up, then what we're doing is that for every two copies of A, we want to cancel them off with three copies of B. So what you do is for the first copy, let's say we cancel off, the second one we skip, and the third one we cancel off. So if we keep on doing this, then if this happens for all blocks, then we know that A to the 2n is and is equal to the number of B to the 3n. Um, yeah, so that is what we're doing from this point on. This one we are popping off the first B, second B we are skipping, um, and then we are popping off again. So after doing this, if the stack is empty, then you know that there are the number of 2 times number of A's is equal to, yeah, basically this thing. Okay, and uh, yeah, and there could be like this same thing could keep on happening over and over again, so this loop is going to take care of that. uh, One copy of B we are skipping and two of them we are um, popping off. Okay, and in the end, if the count matches, then we will go to the final state Q5 and accept.
Yes, yes.
Ma'am, I have a question on that topic of PDA. So
Hmm.
can I continue?
Yeah.
Design a PDA for odd length palindrome for the language L equal to within curly brace W C W to the power R such that W belongs to A B A comma B closure, and so the representation for final state PDA and empty stack PDA, consider W to the power R is the reverse of W.
Okay. Sure. So yeah, so then what you do is until you see a, okay, idea would be that you keep on sorry, keep on pushing the elements of W. So this is W, these are basically elements of AB. You keep on doing this, and then when you see a C, you know that the C is kind of telling you that you have reached the middle of W. Okay, so when you see a C, you don't do anything. Okay, just skip over that. And now, when you start seeing, yeah, when you start seeing the reversal, okay, you know that you have started seeing reversal because you encountered a C. So then what you do is when you read the first element of W reversal, you're going to pop off one element um from the stack. Okay, and you keep on doing this. So, and they should match, by the way. So if this is an A, then this better be an A. If this is a B, then this should also be a B. Okay, and yeah, and you keep on doing this. So that is what is happening, right? You are accessing um, the W in the reverse order here and checking if it matches with the W reversal. Is this fine, or should we
Uh,
write?
uh, I think more explanation required. So, what is mean by final state or empty stack PDA? Can you explain?
So yeah, so there are two kinds of notions of when do you say that a PDA accepts a string. Okay, and both of them are equivalent, so either of them is okay. So what we were doing here is that we were accepting by empty string. So when you have reached um, yeah, when you reach the end of the input and you have ended up in a final state, then you accept. So that is what was happening here. We have reached the end of the input and we have landed up in a final state. uh, yeah, go ahead,
Okay,
correct
okay.
me if I'm wrong.
Yes, yes.
Yeah, and the
Yeah.
other thing is acceptance by empty stack. So I'm guessing you should have ended up with the input and you should have emptied the stack or something. I don't remember. Yeah, can you?
Yes, yes. So in the empty case, in the empty stack, the entire input has been exhausted. Entire input has been scanned, and now nothing is there in the stack, and quite possible that we may not have reached to the final state. So even if we reach to the non-final state,
Hmm.
if nothing is remaining there over the tape and nothing is remaining in the stack, then also they consider that the string is accepted.
Hmm.
And moreover, we can draw the PDA for his problem, and that won't be difficult. The WCWR, which he said. So if we start from the initial state and uh, like say yeah, and so if we read a comma z naught, then I push yeah, a, yeah.
A comma z0, then we push it. If you see
Yes.
b z0, then you push it. Yeah. Okay, these are so many cases, but
No, no, there would be six cases,
hmm.
not one. There would be six cases because
Yeah.
this design used to be so very symmetrical. Yeah, so so A comma A, yeah, and then A B, yeah, A push A, and then B comma A, so B 3, and then 2 5. One is remaining, B comma B, and then push B, and then if we read a C, so then C comma A, so then I will skip it.
So
So
many,
C comma
yeah. There are so many cases here as well, because
there's two cases only, and at the most there could be three if W is
is
null. So
yeah.
then the simple C would also become the
Yeah,
part of it.
let's assume that the length of w is at least one.
Yeah.
Yeah.
And then to the next state Q1. At this point, I should get the combination of A comma A and B comma B only, because that is the reverse of the W. So if it is A comma A, then I pop it off, and then B comma B, then also we pop it off. Instead, I mean, we can, and then after reading a null comma Z naught, and then we make a move to the final state. We can easily include the C comma Z naught here as well, just to incorporate, just to include that fact. The English single C is also the part of the language. So here C comma Z naught, then I will skip as well.
Sure.
So yeah, C comma Z naught. I mean at this point, yeah. And so this is the acceptance through the final
Final
state.
state.
Now, in case of empty stack, probably they can we can erase this Z naught here, and then Q2 need not to be the final state.
Hmm.
Then also the
Hmm.
string would be.
I have another question. So construct a PDA accepting a to the power n and b to the power m, a to the power m, such that m comma n greater than equal to n by null state.
By null state, as in a to the n, b to the
b to the power
n,
m,
right?
a to the power n again, and so m comma n greater than equal to 1 by null state.
What do you mean by null state?
uh, Construct a PDF accepting this language L equal to the sum a to the power n, b to the power m, and b to a to the power n, such that m comma n greater than equal to 1, close curly braces, and by null state. But
Null
here the
stack will
question
mean
Null.
the empty stack
empty,
actually.
empty. Yeah, yes, yeah, yeah.
Null
So
empty stack is
yeah,
also
so
null stack somewhere.
you want the acceptance to be done by empty stack rather than by final state. Is that the question, or
Empty stack. Null state means empty, empty.
yeah, I mean basically that's just the acceptance condition, right? That has nothing to do with the language, is what I'm asking.
Yes, yes, he mean to say empty stack only, and there is nothing to share.
Okay, yeah.
So
Okay,
here,
so then yeah, then basically you just need to skip over the b's. You just need to make sure that there is at least one b, and then push all the a's, and when you see a b, you just skip over them, and for the remaining a's that follow, every time you see an a, you keep on popping one of these. In the end, you should end up at z0. So if you are at a z0, then push it. A also, you push it. If you see a b, Uh, yeah, BA we're going to skip. Furthermore, if you see more BAs, we are going to skip. And now if you see A, then we pop. Oh, you don't really need a new state for that, but it's okay. Let's just in the end, if the string is empty, you want the top
Yes, yes, yes.
is this okay? Is this does this
Yes, ma'am. I satisfy with your answer.
oh good. So hmm. Okay, like um okay. So one thing that I'll not prove, I don't know if you've seen this in the class, but one thing to remember is that if you have a context free language, L, then you can equivalently come up with a PDA which accepts that language. And similarly, P, uh, if you have a PDA M, then the language of M must have an equivalent context free grammar. Okay, so one example that you have seen earlier is A to the N, B to the N, C to the N. We know that this is not this is not a context free language. Okay, so so equivalently you cannot come up with a PDA for accepting this language. So in case of regular languages, you have what we had two ways of showing that a language is not regular. So what are those two ways?
For the regular, those were the pumping lemma and the Mahilner rule.
Correct. So if a language is not regular, then either you have a pumping lemma or you have a Mahilner rule. And pumping lemma was somewhat weaker because uh, if a language is not regular, then you can use pumping lemma to show that. But if a language is regular, you can't use this. But whereas this was stronger statement, which was that a language is regular if and only if certain properties hold. So you can use it in both directions to show that a language is regular or to show that a language is not regular. But in context of PDAs or CFGs equivalently, the pumping lemma for CFGs is for CFLs. That's also a weaker statement because what it says is that if L is a CFL, then it must satisfy certain properties, right? Then it should satisfy certain properties. So if you have to show that a language is not CFL, then you will have to show that these properties don't hold. Okay, so this is the statement of this is very similar to um, the pumping lemma for regular languages. So let's say P is the pumping length. So for all W in L, length of W is at least P. Yeah, and also like similar to the pumping lemma for regular languages, it only makes sense to apply it when the language is infinite. If the language is finite, then you can always come up with a DFA for it. If you can come up with a DFA, then definitely it's a CFL. So yeah. Mm, that
Can we can we
exists.
start, can we start from there exist P? Because in the pumping lemma also we wrote if L is
Yeah.
CFL, then there exists a P, a pumping length, such that for all W's, yeah, W is greater than this, and then yeah, alternatively, I mean these would be appearing. So now then there exists UVWXYG, right, right, yes.
A partition UVWXY. Um, so sorry, this is overwritten. Mm, Let me call it.
So there exists
This
S.
X.
S is the element of L, wherein the length of S is greater than or equals to P, such that now this U, V, W, 3 and then 4 and 5. Yes, yes. Now it's okay.
Hmm. Yeah, this is basically the string S, some partitioning of S, such that um, for all I greater than equal to I comma j greater than equal to 0, u v to, sorry, you don't need an j, yeah, u v to the I w x to the I y is in L. Sorry, is
Yes.
that j or is that I here?
Both, I mean, yes, yes, I. Any number of V's and X can be pumped in. Yeah. U V raised to the power I, W X power I Y is also, I mean, would also belong to the language. And additionally, we can write those two inequalities here
Right.
along with the
The
computation.
Yeah, the
So
length of.
those, yeah, length of V, I mean, length of VW and X is collective, their collective length is less than or equals to P is one thing. And the collective length of V and X is greater than,
Yeah,
not equal to,
vx
greater than,
is at
yeah.
least 1.
Yes, greater than or equals to, yeah, one, right. Non-zero,
Hmm.
I mean non-zero.
Yeah. Yeah, so if you want to show that L is not a CF, a CFL, then you will say that no matter what P you take, there is always a string S in the language whose length is at least P, such that no matter how you partition U, V, W, X, Y, uh, satisfying VWX is at most P, Vx is at least 1. There exists I greater than equal to 0 such that U V to the I, Wx to the I, Y is not in L. So all the negations become for all and for alls become there exists.
Yes, yes, yes.
Okay, so this is the form in which we will use the pumping lemma to show that a language is not regular. So, a simple example, yeah. Okay, let's take L2. L2 is A to the N, B to the M. Let me bring this thing here so that the lemma is also visible. But maybe I'll just. Hmm.
So we take a long string, say a raised to the power. Oh, M and M are they're different. So Okay. Equal number of A's and C's and equal number of B's and then D's. So if we need to prove it using the pumping lemma, uh, so then what is the relation in between this thing and there exists a pumping length P? Because it would be inappropriate to consider a string a raised to the power p, b raised to the power p, c raised to the power p, and d raised to the power p here. And then I can easily apply the pumping lemma to show that if I pump some of the v's and the y's, that will disbalance the string. So, but then I can take q here, right? And so if c raised to the power p and then d raised to the power q. Uh,
But you're going over all p's.
yes, so, I mean this in this sense, this problem is slightly strange because we do not know anything about Q now, isn't it? Except that Q is greater than or equals to 0.
Hmm.
Or do we know any
That's fine.
relationship in the P and Q?
No, that's fine. We don't need it. I don't think we'll need any relationship because we are actually going to uh, use these two constraints as well. So VWX part can, I mean, it can either contain only C's, or it will contain some B's and some C's, or it will contain some C's and some D's. That's all.
Yes. Yes. There
So
would be
that
finite
helps
number
the
of
analysis. Hmm.
yes. So if you consider all possibilities, so then if U is null, then entire this VW and X will contain, I mean, will be confined to A's only. And then if I pump more, what that notation is, more V's and X, that will disbalance this entire string.
Yeah. So you're saying if VWX is entirely here,
Yes.
that's the
So
first
there are,
case. Huh.
yeah, so there are two possibilities. Say if V and X contains only one symbol. So if V and X contains only one symbol, so that possibility would be that either we limit ourselves at, I mean, within A's only, or we go ahead. But then there could be a possibility wherein this V and VW and X, maybe they are inside B only. In case if Q is greater than P, if he makes any assumption about Q, so what is the chance? I
So
mean,
are you looking at this case where are you looking at this case where where VWX is here, something like this?
no. The entire VWX is there inside B's only, and
No.
you may, I mean, you is getting contained. I mean, you has consumed all the A's, and VW and X are there inside B's only. Because that would be the case wherein if I pump any number of the V's and the X, so that will not disbalance the string would still belong to
That
the.
will still okay. So let's first do this case. Uh, this case, the second case is going to be very similar because okay, what is the issue here? If all the entire of VWX is contained inside A, then if we pump more A's, you will get A to the P plus some n, B to the Q, C to the P, D to the Q, and now we are violating the fact that number of A's here and number of C's here should be the same. So this will not be in the language. Okay, same thing happens here um, if VWX is entirely contains B's, then if you pump more number of P's here, then you'll have A to the P, B to the Q plus N, C to the P, D to the Q, and now here you have created an imbalance. So this
Yes,
is,
yes. Right, right.
yeah, but even before this case, what would happen is if it's contained, like we are shifting it slightly to the left. So first thing is it's entirely in A. Second thing would be it has some A's and some B's. Third thing would be it has all B's only. So let me make it 3. A to the P, B to the Q, C to the P, and VWX is some A to the P prime and B to the Q prime. So now what is the issue?
So like here, if we pump, so we would be having AB kind of a thing. But in this system, we can have a single AB. So that will also be a disbalance.
Exactly. So now if you pump, what will happen is you have some number of A's here, then you have some number of B's here, then you'll have A to the P prime, Q to B to the Q prime, and so on. You'll have strings like this, but this violates the structure of the string itself, because after seeing A's you can only have B's. You can't have B's followed by A's and so on. So this is also not in the language. Then this was our third case, that it is entirely it entirely contains B's. Third case would be that, sorry, fourth case would be that it contains some part of B's and some part of C's. In that case we'll end up in a situation like this. You'll have BC 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 sort of thing.
Yes, yes.
And finally the case is it's entirely in C. Again you'll have similar arguments.
Yes.
So yeah, it's like a lot of cases, but the analysis is exactly the same.
Yes, and we would be having finite number of the cases, and
Hmm.
yeah, finite number of the cases. Right.
Hmm. Yes. Is this okay, Saurabh?
Yeah, ma'am. Now just the new chapter and for me, so I'm just thinking a little bit. Take time to thinking. So just I get a some viewpoints and get, so collectively I will let understood better, and if some time will taken.
Sure, sure, sure. So let's try out. This one would be easier. Like this should follow from this, I guess, right? Yeah. So let's skip L3. Yeah. Let's do L4.
I think L4 is also no different.
Hmm.
Similar logic. A raised to the
Okay.
power p, b raised to the power 2p, c raised to the power 3p.
Yeah. 1 second. Yeah. Is Oh, okay.
It was not 3n, it was n only, right? Yes.
Huh.
Yes,
And
yes,
only.
it is right here. Yeah. So we consider the strings a raised to the power p and b raised to the power 2p and c raised to the power p. And by using b raised to the power twice of p, will it restrict the number of the possibilities further compared to the previous one, wherein we were having the possibilities like only a's and then
Hmm.
ab and then b's and then
Hmm.
bc and then only c.
Hmm. Yeah.
Since we have b raised to the power 2p here, will this change situation?
Yeah, I mean, these are definitely lesser number of cases than earlier, because either it's all A's, or it is A to the P prime, B to the Q prime, or it is just B to the some, yeah, some number of B's, or some number of B's followed by some number of C's. That's all.
So then this entire logic would be same. I mean, we have same
Yeah,
number of things. By the way,
exactly.
you use different notations, I guess. Not this is not UVW. I mean, in the slide you use the
Oh,
notation
right. This is WX,
V VWX.
VWX. Yeah,
Yeah, yeah.
yeah. These two cases are same, and then these two cases are same. Yeah, same as in terms of analysis. Yeah.
Yes,
Mm,
yes, yes.
hmm.
So in this case, uh, WW. So so I can. I mean, which string should I take here? WW and. So I guess I can take that 0 raised to the power p, 1 raised to the power p, 0, 0 is okay. This is AB. A raised to the power p, b raised to the power p, and then a raised to the power p, and then b raised to the power p. Or will this impose some kind of the constraint, or is this not the right? Is this not the right way of selecting the string, or is this
Are you,
correct?
yeah, what is your string? A to the P?
B to the p, and then a to the p, and then b to the p.
Yeah,
This is the
this,
part of the left.
yeah, this should work because, I mean, anyway, we are exhibiting only one, I mean, one string here.
Yes. So if that is the case, then here the things are easier. Things are easier,
Hmm.
and yeah, yes, yes, yes. So
Yes.
we can show that, I mean, finite number of the possibilities, uh, and the pumping will disbalance the string
Hmm.
in all the cases.
Hmm.
Yes.
Yeah. Mm, yeah. Hmm. Okay. Okay. So, consider a variant of this model PDA. We'll call it a PDA where instead of a stack, let's say you're given a queue. So in stack, what you do is you always push at the top and you always pop from the top. Whereas in the queue, what you'll do is this is your stack. You're going to push at the top and you're going to pop from the, yeah, you're going to pop from the bottom. This is, yeah, exactly how real life queue works. People line up here and new people keep coming here, and this is the order in which people start, um, yeah, leaving. So now you think of the same model that we had earlier, but instead of doing operations in stack, you'll do operations in queue. So whenever you push, you'll be pushing here, and when you pop, you'll be popping here. So one one simple language that you can simulate using this new model is WW reversal, um, where let's say W is in 0 1 star. Mm, okay, yeah, sorry. I think you need some kind of a demarcation for where this C lies. Okay, so then what you'll do is, mm, so this is, sorry, yeah, I guess it's easy with WW. So this is, if you keep on pushing, you have WW1 and so on up to WN. Um, in the end, when you see a C, you sort of know that you have reached the end of W. And now what you'll do is, um, when you pop, you're actually popping from here. So read W1 and pop from here. Now W2 becomes the bottom, like, yeah, the last element of the queue. Then you read W2 and pop W2, read W3 and pop W3, and so on. So basically, you are checking whether each element here matches with, yeah, matches with the last element of the queue. And that's how you can check if the string here and the string here are the same. But if you're not given this demarcation that this is where the middle is, then you'll probably have to guess over. Yeah, yeah, maybe you'll need some kind of non-determinism here to detect where is the mid of that string. But yeah, that is one simple language that you can see easily that okay, this is accepted by this new model. Is this okay? uh,
Actually, this is not. Uh, I could not understand this because we used stack in the PDA
hmm.
in the hope of including a memory element, which was not there in the finite automata. And stack is a memory element. But how can I consider Q as a memory element? Whenever I need memory, even in the data structure, when I need memory, I mean, whenever I want to postpone my decision for a while, I go for the stack. Q does not have a memory element, I guess. And moreover, now in
No,
this,
Q is also memory because at the end of the day you are storing some sort of information into it, right? In fact, you would have probably seen these implementations of queues using two stacks.
right, right. So, yeah. So, which languages are being accepted here? Because now I mean, in this definition of the PDA, the pointer is pointing to the top of the stack. So now where this pointer is pointing in this queue, top of the stack, or still pointing to the top of the stack. So I
There
read
are two
here.
pointers that you have now. We can't, yeah, we can't do this with a single pointer. There is one pointer that tells you this is where you're going to push. There's another pointer that tells you this is from where you're going to pop.
Oh, I see. So would it be similar to the Poisson automata with the two stacks? There is also a variation of
Mm,
the PDA available, the PDA with the two stacks. And in case if q, so because I would be maintaining two pointers here, and the definition then needs to be changed. I mean, the transition function, etc. Other
hmm.
things also.
So whatever you can accept using this, you'll also be able to accept using two stacks. But the other way around may require some argument. It's not immediate. Because yeah, Q you can implement using two stacks. So that direction is fine.
Okay, okay. All
Yeah.
right.
But yeah, but right now maybe like for now maybe not going into its philosophical thing. Like let's just think of it as an abstract. I mean, some model that you are, and you have to work with it.
So
We just want to,
yes,
huh,
yeah, yeah. Please continue.
yeah. So um, yeah. I mean, just as a variant of it, let's just try to understand the um, yeah, power of it.
So instead of W1, W2, can you write an actual string like say A, B, something? So then it would be easy to understand that how this
So
WCW is going to be recognized. Let us take W is equal to A, B.
yeah, let's say this is 0 1 alphabet. So let me
Oh,
say 0 1 0 1 0, and then you have C followed by 0 1 0 1 0, and so you had, yeah.
yes. So initially I push everything,
Hmm.
right? And then I will read a C. So when I read a C, and then I keep the things as it is, and then I read a zero from the tape.
Hmm.
So then I will make a pop. Pop will be made from the end, and then zero one.
Hmm.
0 1 0. Yes, yes, you're right. Yeah, WCW will get accepted. Right. Yeah.
Okay, so let's try out this other thing. This is somewhat more interesting. Um,
What
so
was the question, by the way? In this question, what was asked?
yeah, you want to check whether this model can accept this language.
Can you show the question? There was, yeah, what was there?
Yeah, I mean this was different, but yeah.
Okay. The W square and then oh, all right, fine. So a two raised to the power n. Okay. So if I put n is equal to 0, then a, and then a square, and then a2 raised to the power 4 in that sense. So I push a. So like say 4 a's. This is or 2. Yeah. So since perfect pairing can be done here, so whenever I read an a, I push the things and I pop the things. So everything would be done in a pair. So like say
Um,
I push I what are the some of the valid strings for this language that we say a.
mm-hmm.
This is an exception only a, and then otherwise it would be what 2a, or then
4
4a's,
A's.
and
Yeah.
then 8a's, right? So this Q system, this modified PDA, would be able to recognize this language. Yeah, would be able to recognize.
Hmm.
When I read a, I push it, and then when I read one more a, I pop it.
No, but
Yes.
then that will be what you are doing is you are um, accepting this language. Sorry. Uh, how do you write this? And one where basically I'm saying you are accepting all even length strings.
Yes, right. Right. But this problem is slightly different. So I mean, it should accept a raised to the power 8, but should not accept a raised to the power 6.
Hmm. Yes.
So if that is the case,
property about power. So this is basically power of 2, right? So one property about power of 2's is that if you keep on halving it, eventually you will reach 1. If the number is not, I mean, so if, okay, so let's say you have an input n, and what you do is you do n by 2, okay, and you, if n is not equal to 1, then, okay, and you keep on repeating this, or um, hmm. Okay, let's say I'll stop it at 2. Let's say I stop it at 2. Okay, so what will happen is if you have a number which is a power of 2, you divide it, you get a power of 2, you divide it, you get a power of 2. Eventually, you will end up with 1. But let's say you started with an even, any number which is not a power of prime, you keep on dividing it by 2. Eventually, you will reach a number uh, which is odd but not 1.
Yes.
Okay, so that is one property we can use here. So how, so the question is from A to the, okay, let's do this thing. You have you have been given a string, okay, and you have pushed it entirely. Okay, now you want to do something, some operations here, and get a new configuration where if n was the number of a's here, then you want n by 2 number of a's here. So if you can do this, then keep on repeating this process. In the end, you should end up with just one element, and then you would know that okay, the number of a's were a power of 2 to begin with.
Yes, yes. Right.
So the only thing you need to do is find out how to get from n number of a's to n by 2 number of a's. This is similar to what we did today, earlier today, when we had this example, this thing. There was some kind of matching that we needed to do, so we carefully decided what to skip, or equivalently how many copies to push. So what if I,
So when I push an A, I shall. But how to make the things half?
hmm.
That is not actually clear.
So if you remove two a's and you add one a, so you
But
remove,
then initially there would be just one A. In the very first string would be A. A should get accepted because A is a part of the language. N
so
is greater
what you
than.
did is first you did like you pushed everything. The entire string is in the queue.
Okay.
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 Now you pop two a's from here and push one a here. Okay. So for example, let's say you had 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. 8 is here. Okay, then what you will do is pop, sorry, pop 2 push 1, pop 2, push 1, pop 2, push 1, pop 2 and push 1. Now you are left with exactly 4 number of ways.
Yes, but then the thing is that without reading things from the tape, how can I push something into the queue? I mean, say if four A's are given, I mean, whatever I want to recognize is placed there over the tape. And then and then I have pushed entire stuff into the queue.
Hmm.
And then from where would I bring the elements to push into the stack? Hypothetically, that okay, whenever so it would be the combination of null comma A.
Right. Yeah,
So
so
if it is null comma A, then I will push certain things into the elements.
hmm,
Oh, in that sense, yes, that can be done, right? Yes.
hmm.
Then it's true that when I pop an A, then when I pop two A's, then I would be pushing one A corresponding to the pop of the two A's. That kind of the looping can be done. Then I'll remain half of the thing. So then, I mean, yeah, yes, this can be done, right?
Yeah,
Yes.
you keep on doing this. Eventually, you should only be left with 1A.
Right, yes. And what's the name of this PDA? This variation of the PDA. I mean, something was
I don't
given
know if
PDA.
this is I don't know if this is a standard name that's
Uh,
there, but yeah.
Put through Automata. Okay, okay, right, yeah.
Hmm. Okay. Yeah, I think that is all the questions I had for today. But if there are any questions that you have about
My,
the
my I have a question on the topic of PDA. So design a PDA for the language L equal to a to the power within a curly braces a to the power n b to the power n union of a to the power n b to the power 2n, so such that a main greater than equal to 0.
uh, this is what you mean?
Union means both conditions accepted.
Union, I mean, in general, union means like one condition accepted or the other condition accepted. So,
Any one condition is true, then both condition will be accepted within a set.
mm, I don't understand exactly what you're saying, but
Probably he said something. A raised to the power n, b raised to the power n, union a raised to the power n, b raised to the power 2n. You said 2n, or is this right?
or is this what you are saying?
No, my question was a to the power n, b to the power n, union a to the power n, b to the power 2n,
Yes, yes.
2n.
such that m n greater than equal to 0.
Yeah, so what I'm saying is it does not make sense to write like, I mean, it's not correct to write like this because when you say union, you talk about union of two sets. So this is this is probably what you meant. I mean, does this capture the language you are looking for? So L is the set of all strings that are of the form either there are equal number of a's or a's and b's, or the number of a's is exactly half the number of b's.
Can you repeat, please?
Yeah, I'm saying, so you want the language to contain all strings that have equal number of a's followed by equal number of b's, or n number of a's followed by double the number of b's. Either of that should be in
Yeah.
the language.
Yes, yes. This is question. This
Yeah,
is my
so
question.
what I was saying is, you don't write it like this because, I mean, this is not a set by itself, right? So whenever you say union, you mean union of sets. That's it. Yeah. So you want to come up with a yeah, is this okay?
Yes, okay.
Hmm.
But
So
I require a PDA. Construct. How can we construct the PDA?
So if we have PDF for L1 and PDF for L2,
hmm,
and because when we show the union of the CFLs, we show it at the level of grammar,
hmm,
not at the level of machine.
hmm.
So now in this case, how to design the PDA? How to design the PDA that the number of B's may be same as the number of A's,
Hmm.
or maybe the double of the number of the A's. So probably we could. So after getting A comma B, when I get the, I push all the age into the stack. When I read the combination of B comma A, then I would be having a choice either to pop it off or keep A as it is and then pop another A off in the next round. So that would mean that uh, I can use epsilon moves here, and then by using the epsilon moves, I some kind of the non-determinism I use. Yes, and NPDA can be made. NPDA can be made.
Yeah, but I yeah, I don't think NPDAs are same as PDAs, because NPDAs can capture languages that PDAs cannot capture.
Yes, yes, right.
So yeah, but yeah, how do you take two PDAs and make a union out of it, right? Mm. Well, in terms of grammar, it's kind of easy to see. Uh, okay, one thing that is not direct is that you first um, get the pencil charge. Okay, one very non-direct way of doing this would be, you know, um, you have, I mean, you know the grammar for this, right? So yeah, and B is yeah. Okay, then there is something called equivalence of grammar to PDAs, where given any grammar you can convert it into an equivalent PDA. So what it does is that um, it starts with S on the top, okay, and then it yeah, okay, and this has to be brought into the CNF form, the Chomsky normal form. Only then you apply this construction. So any grammar can be brought into an equivalent Chomsky normal form. Now you look at that and you apply the rules. So whenever you see a non-terminal, you pop it off and you push the um, production corresponding to it. Whenever you expand it, let's say maybe B gives A or something. So whatever terminals you see on the top, you are going to pop it off, look at what is on the top. If it's a non terminal, you expand it and keep on doing this. In the end, you should end up with an empty stack. So this is roughly the idea behind converting a context free grammar to a PDA. But so if you do that, do those steps, you will end up with a PDA. But let's not do that. Let's try to directly come up with the PDA here. Okay. So
Uh, so at least we can design PDS till a raised to the power n, b raised to the power n
first,
first.
yeah, yeah.
Let us do that first, and then from where probably
Hmm.
we can get a clue that how to make an epsilon move so as to recognize the other form as well.
Hmm. But the problem is, if you when you do this, when you come up with the PDF for this, you first push all the A's, then you pop all the B's, then you don't have access to the string anymore. So how do you?
So, but then, no, no, no. So the thing is that for this language, what are the valid strings? So valid strings could be AB and A comma and AB is a valid and ABB is also valid. So PDA has to be designed so that it not only accepts AB, it also accepts ABB. So when all
Correct.
the B's have been consumed, in the case of the ABB, then I would be reading one more B,
Right.
one more B from the tape, and then I would be reading Z naught as the top of the stack.
Then you would also end up accepting um, A B B B.
Yes, something can be done. I mean, probably
Hmm.
because so
Mm.
can't we use this fact that we can have multiple final states? So we make this as a final state. And if I read the combination of say B comma Z naught, then I make a move to the state. Yes, that can be done, I guess. The
Mm.
only thing
Okay.
is that, yeah, so we would be requiring two final states, not two final states, but then we would be requiring, so then, yeah, null comma Z naught, null, and B comma Z naught. So by Z naught, and then when I read one more A, I keep on moving it here. I think, yeah, we can do it. We can do it. Uh, so from the self loop, when we keep on erasing, uh, I mean, A is corresponding to the B's, and we move towards the final state. In the case of the A raised to the power n, B raised to the power n, then from that state, I need to fork, I need to create a branch, and by taking an epsilon move, and then I can scan whether I am having that thing or not.
Yeah. The only issue I have with that is if you take an epsilon move, then um, yeah, then you are sort of using non-determinism here.
Yes, yes. So I mean, because this quite quite possible that this CFL is not a deterministic CFL because a very small subset of the CFL is DCFL, for which DPDAs can be designed. Most of the CFLs are, I mean, for them we design NPDAs only. For large, for large family of the CFLs, we design DPDA, sorry, NPDA only.
Oh, okay, but I mean, isn't it true that CFLs are equivalent to DPDAs.
Yes, CFLs, no, CFLs are not, I mean, we use the term DCFL. DCFLs are the CFLs for which we have a DPDA.
Okay,
And the general thing is CFL. We do not call them NCFL kind of thing. General thing is
okay.
CFL, and for them we have this NPDA.
I see, I see.
Yeah, yeah, yeah.
Okay, so that is maybe that is what this thing is doing. I mean, it's basically doing
Yes,
the branching out for us.
yes, yes.
Sure.
So yeah, so in that case,
Yeah.
some epsilon moves would be required. One epsilon move would be required, and then we
Hmm.
can find it. But we do not have, I mean, a product automata kind of the thing at the, I mean, for the PDAs. We do most of the things at the level of the grammar in CFLs, not at the level of
Hmm.
machine.
Hmm. Yeah. Hmm. Okay. Yeah. Is this fine?
So I did not fully understand the way of you explain it, but I remember some of it in the deeply understand for later. So I have asked one another question. So can I ask you?
Yeah. Sure.
So design a PDA for language L equal to within a curly brace a to the power n, b to the power n, a to the power m, b to the power m, a to the power l, b to the power l, such that m l greater than equal to 0.
Mm, okay. So this should be same as what we did earlier, right? So you push all the A's, then you pop all the B's, then you should be left with empty stack. Then you push all the A's, pop all the B's, and you should be left with empty stack again. Then you push A's and push B's again, and in the end again you should be left with empty stack.
Okay, okay, okay. Nice. Thank you for simplification.
Sure. Okay, so it's almost 9. Maybe we'll break for today. Next we will meet on Monday 7 p.m. to 9 p.m. and we'll talk about Turing machines. Okay,
Thank you so very much. Thanks, Ethan.
thank
Bye.
you.
Good night.